This oval of icons will act as a roadmap for our discussion. The discussion will start with a brief review of the Space Shuttle Challenger disaster.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
So what went wrong? What were the flaws in this decision process? The Rogers Commission wrote a very interesting report on these questions. They found that the cause was the failure of the field joint O-rings. And there was another finding that really intrigued me as a statistician. A careful analysis of the flight history of O-ring performance would have revealed the correlation of O-ring damage in low temperature. Was NASA doing data analysis by rhetoric? Let's look at some of that data again and replay the discussion between Thiokol and NASA.
What about the flights that had zero thermal distress?
Well, that data is not relevant to the question of the temperature effect.
Okay, I guess you're right.
Well, were they right? Here are the flights with zero thermal distress. Notice that they were all at warm temperatures. In fact, above 65 degrees, there were 3 out of 20 flights, or 15%, had distressed O-rings. But below 65 degrees, there were 4 out of 4 flights that had distressed O-rings. So it appears that temperature did affect the probability of O-ring damage. So NASA forgot the zeros, and that was a big mistake. Furthermore, NASA did not do a risk analysis of the O-rings. But would that have been possible? To prove that it would have been possible, on behalf of the National Research Council, Belcore Statistics Research and myself did an actual risk analysis of the pre-Challenger O-rings. I call this the missing discussion. I want you now to pretend that you are a participant in the teleconference the night before the Challenger was launched and have to make a launch decision based on this discussion. Primary O-ring erosion. Now this is different than the data that we used before. That data included all O-rings and all kinds of thermal distress. So here we have the plot. The joint temperature is here. The number of eroded primary O-rings is on the y-axis. Each point is a flight. Here we include the zeros, and the temperature trend is beginning to emerge out of the data. But to figure out what happens at 30 degrees, we have to develop a statistical model, or to predict what's going to happen. Now, our prediction is the yellow curve. The green curve represents the uncertainty in our prediction. So the predicted number of eroded primary O-rings at 30 degrees is 5.7. But since there are only 6 O-rings, that implies a probability of 5.7 divided by 6, or 95%. So we plug 95% into the formula to solve the first problem. So the probability of any field joint failure is actually the number of field joints multiplied by the probability per field joint. And this is equal to 6 times the 0.023, which is 14%, or 1 out of 7. Now, ladies and gentlemen, 1 out of 7 is like Russian roulette with 7 chambers. Count them. 1, 2, 3, 4, 5, 6, 7, and 1 bullet. The high probability is due to a cold temperature, so we must delay the launch at least until the temperature warms up. Now this marks the end of the missing discussion field. So in developing your risk management strategies for the 90s, remember Richard Feynman's poignant advice in the aftermath of the Challenger. For a successful technology, reality must take precedence over public relations, because nature cannot be fooled. I hope that we've laid out a flight plan to that reality. Thank you for your attention, and have a nice day.